Hello YouTube and welcome to What the Math. Today's video is going to be all about black holes and specifically facts and misconceptions about them. And also at the end of the video I'm going to try to create a massive solar system of black holes. Or would that be a black hole system? Black system? Hole system? I don't know. Basically everything will become a black hole. So let's start with the first fact or first misconception, and that is what happens if our sun became a black hole? So a lot of people actually think that if our sun became a black hole, it would actually suck everything in. And that's not really true. Actually, that's not true at all, because the mass of the black hole sun would not change. It would still have the same mass, so everything around it would still orbit in the same way. So actually, let's go ahead and create our first black hole using the sun. So here's the sun spinning really fastly. Now here's a trick to do this in the game. If you want to create a black hole out of basically any object in the game, you have to decrease the time. You have to decelerate the time until like it's in milliseconds. And then what you do is you set this mass to be constant, so mass will not change. And then you decrease radius. You start decreasing radius. And essentially what starts happening is, well, our sun decreases in size, its density increases dramatically, and as the radius decreases, and as the density increases, it starts approaching a super massive and super condensed object. Now, if I were to increase time right now, it would actually, you'll see the radius going up again, very slowly. Oh, come on, radius. Come on, radius, don't be like this. Maybe not. Okay, maybe not for the sun. It happens for the planets, though. For this one, it doesn't seem to change anything. So let's just keep decreasing radius. I'm gonna keep lowering it until it's really small. Now, here's the thing. Any object, not even solar objects, but any object, including you, if you consider yourself an object, can become a black hole. This is misconception number 2, or fact number 2 is that anything can be a black hole. To create a black hole, all you need to do is condense the matter so densely, with such a high density that the light can no longer escape it, because it has very high concentration of gravitational attraction per volume. It's not really a unit, but it's easier to understand it if you think of gravity as a kind of as distributed in terms of volume. And as you decrease the volume and maintain the mass, what you'll create is you'll start creating a very massive object with the same mass, and so its gravity will be distributed very densely. And so this object right now has exactly the same mass as our sun before, but it's ridiculously dense, and it's about to become a black hole very soon. In theory, if our sun were to be condensed to about 5 kilometers, it would then become a black hole. And let's see if that happens in the game as well. I'm approaching the 5 kilometer mark right now. It's about 40 kilometers, 30. Let's see how it does. And essentially the reason why it's happening is, what most people don't realize is that what matter is, it's actually, matter is literally space. 99.9% of matter is nothing but empty space. And if you were to condense this space, oh, it's not happening yet. Okay, the theory behind this, oh, there we go, 3 kilometers. At 3 kilometers, our sun has become a black hole. Excellent, so I can now accelerate time, and we'll actually, in this game, stay stable. It's not going to change anything, it's actually going to maintain its black holeness. And hopefully everything around it will still be the same. Let me just zoom out. And, oh, okay, things went wrong a little bit here. I think it's because something happened to my mass. I don't know what happened to my mass. For some reason, I decreased my mass. Let me just try this again from scratch. Alright, this is attempt number 2. I'm very close to 5 kilometers. Oh, it's so bright. So it's decreasing in size. I think I accidentally unclicked the mass setting in the last time, but I'm gonna try to maintain it this time. So let's see if this happens again at around 4 to 5 kilometers. Essentially, if the radius of our sun were to become 4 to 5 kilometers, this is when it would officially become a black hole. Oh, in this game it's 3 kilometers, but that's okay. Alright, so mass is 1 sun, radius is 2.77 kilometers, and I think that's pretty accurate actually. And here we go, accelerate time, and let's see how our solar system looks. And everything's still in orbit around it, so obviously the only difference would be that now all of the planets will start getting really cold. And this one is already cold. Mercury is already minus 223 degrees Celsius, close to absolute zero, because Now our sun doesn't emit any energy anymore. Now it doesn't actually look entirely black. You can see it has a corona around it, and that's actually very realistic. Black holes are not entirely black, and this is a fact or misconception number 2 or 3, I'm not sure anymore. And essentially the fact about black holes is that they have 2 types of energy. They do emit energy, and there's 2 types of energy. One is theoretical, it's called Hawking's radiation, and that's essentially, it's kind of like black hole evaporation. So black holes actually evaporate, disappear a little bit with time, and smaller black holes, the ones that are not too massive, can actually disappear completely. Whereas more massive black holes, as long as they keep absorbing more mass, they will actually maintain their mass and even increase it, so they won't disappear entirely. But if we were to create a black hole inside our sun, so essentially if this is a sun-sized black hole, it would not last very long because it doesn't have enough mass to maintain its black holeness. It will actually disappear just in a few hours, if even, probably even less than that. If, however, we were to create a black hole out of our planet Earth, which is what I'm going to do right now, it would last even less. It would actually last only seconds because its mass is just very, very small, and it would not be able to maintain its black holeness. It would actually disappear relatively quick. So let's actually do this right now. Let's create a black hole out of Earth. And look at that, Earth is entirely covered in ice. It's totally frozen because of the temperature. And it's only, actually the temperature is only minus 20 degrees, surprisingly. But nevertheless, it's all ice. This is what snowball effect would be like if the entire Earth would basically be covered by ice. Alright, so I'm going to freeze its mass and start decreasing its radius as well. Now, in this game, you'll see that if you don't decrease the time, or basically if I let go of this now, it starts increasing its radius again. So I actually need to decrease time. I need to decelerate my time until I can actually do this successfully. Now, in terms of Earth, it has to be about the size of a marble for it to become a successful black hole. And like I said, it wouldn't last very long. The miniature black holes that we theoretically create by using, what is that thing called? Large Hadron Collider in Switzerland, which is basically a particle accelerator. It's a particle accelerator that accelerates particles moving toward each other at close to speed of light. And when they collide with each other, they actually create a massively super dense particles, which is essentially kind of like similar to a black hole or black hole-like conditions. And we do create those black holes all the time, or at least that's the theory behind it. And people were really worried about it. There was actually a Time magazine article about it saying that this Hadron Collider will destroy the Earth. But that's not true because those black holes only last like microsecond, not even microsecond, they're like miniature part of a second, and they disappear afterwards, releasing energy. Now this energy has not been detected yet. It's still a theoretical energy called Hawking's radiation. We actually don't really know if it even exists, but we do know that something else exists around black holes, and I'll show you that thing in a second when I create a black hole out of Earth. I'm going to do this manually. There we go. Is this a black hole yet? No, it's not. It's still terrestrial. It's a tiny, tiny miniature Earth of 1 meter. So let's keep decreasing this until it's in centimeters. Okay, our miniature cute Earth of 5 centimeters is about to become a black hole. I think it's, there we go. Oh no, I made the same mistake again. That mistake is what I made last time. I accidentally decreased its mass by accident. There we go. Is that a black hole? Are you a black hole? No, you're not. You're not a black hole yet. Come on. Why you be like this? You're being difficult, Earth. You're being very, very difficult. Let's do this manually. Alright, there we go. It was just under 1 centimeter, actually 8.87 millimeters. And now Earth is also a black hole. And you don't really see this near Earth. Let me just zoom in. Yeah, as you can see, there's not much corona radiation near it, but if you go back to the sun, it has a lot more energy-like particles. And this is essentially one of the main features of black holes. As they suck in various mass, or basically particles from outside of the black hole, some particles go inside it and increase its mass, but some particles start orbiting around it really fast. And as they increase their speed, which is essentially close to the speed of light, their mass and their energy increase dramatically. And this is where Einstein's E equals mc squared comes into play as well. And essentially those particles start disappearing slowly and releasing massive amounts of energy. And this energy is called black body radiation. And this black body radiation is probably one of the most, if not the most efficient way of creating energy out of out of mass. Now, if we look at a star also creates energy out of mass by burning, by using fusion and fission, basically inside the star. It's nuclear reaction, in other words. The stars use nuclear reaction to create energy out of mass, but it's only about 0.7% effective. So there's a huge inefficiency in stars. Black holes, however, about 10% effective. In other words, if a black hole has mass orbiting around it, 10% of that mass, following the equation E equals mc squared, will turn into energy. So this is actually one of the more efficient ways of creating energy. And scientists have been speculating about how to use this to create like super powerful spaceships or something of that nature, where essentially you can create a black hole, and then if there's mass orbiting around it, it will release such a huge amount of energy that you can then use that energy for various purposes. Alright, so let's go ahead and create a black hole out of mercury. So we'll do the same, freeze its mass and start decreasing its radius. Now, mercury has to be much, much smaller, probably in less than a millimeter to become a black hole. Now, another fact about black holes is that they're not, some people say that there's infinite density in them. Well, that's not true. One thing we know for sure is that laws of physics do break down inside black holes, so we're not sure what's happening inside them, but they're not infinitely dense. There's a very specific density to each black hole. And when we create mercury, I'll show it to you. Hopefully it actually shows in this game as well. So in other words, it is not infinitely dense. There is a specific density to them. And the more, this is actually a very, very interesting fact, and something that I was, when I heard about it the first time, I was like, what? That's not true. How is that possible? But the more massive the black hole is, the more massive it is, the less dense it is. In other words, if a black hole is really, really massive, if it's like, let's just say it's like 1,000 mass of a sun, or even a million times of our sun, it will actually be less dense than the sun. Our sun black hole is a lot more dense than a massive black hole. You've probably heard about the super ultra massive black hole in the center of our galaxy that essentially causes all the stars to fly around it. Now that particular black hole is something like, I think it's about maybe billion mass of a sun. It's essentially, it's huge. It's just super massive. Now, the interesting fact about that particular black hole is that it is less dense than air on our planet. It is actually less dense than air. So let me just give you a visual comparison. Oh yeah, there we go. Mercury is 0.00049 meters, which is, what is that in centimeters? Is that like, I think it's like 0.4 millimeters or something. And I think, okay, this shows you density. It's 6.91 times 10 to the power of 29. And if we look at our sun, where's my sun black hole? So hard to see now because it's so black. Cannot see them. I need to zoom out before I can see it actually. Let's compare their densities. So this is Mercury. Then the next one was Earth. Where is Earth? Oh, there it is. And Earth density is about 100 times less dense. And then Sun is about, what is that? 10 to the power of 11 less dense. So essentially it's not dense at all. Now, the super ultra massive black hole in the middle of our galaxy is less dense than our air. What this means is that, let me just accelerate time so I give you a visual perspective of this. If we were to create a black hole, that is approximately, where's Neptune? Let me find Neptune. There it is. That is approximately this big. This is approximately this big. So basically, a radius of from Neptune to the Sun. So this is the size of our imaginary black hole. If this is a black hole, which is possible, if you combine a lot of mass together, this will be a really massive object. Its density will actually be exactly the same as density of air on Earth. So essentially, if we were to fill this whole volume with pure air, with air of 1 atmosphere, it would actually become a black hole. And this is just mind-blowing. So this would be, I don't know why it's shaking. I think I'm actually zoomed in on the Sun. I'm going to zoom in on Neptune. If this is a black hole, it would actually be air inside. Now, can we live inside? Well, I don't really know. It's the physics break down in black holes. Things don't make sense anymore. You can divide by 0. You can do some crazy things. So we don't know if you can live inside, but it's possible to like have a black hole that's essentially filled with air. Anyway, so let's keep going. Let's create some more black holes. I think our sun moved a little bit. Next on the list is Venus. Venus, you're going to be another black hole, pretty orange black hole. And let's talk about another fact. Okay, so I'm going to do this manually. Decrease Venus to approximately a few meters size. And start. Oh no, it's growing back. I didn't decrease my time enough. Okay, good. There we go. And the fact number, I don't know, 4 is that black holes they don't just have mass, they have 2 more features. One of them is electric charge, so black holes can actually be charged just like, things that are charged, like if you rub your hair on a balloon, you become charged. So black holes can have the same, they can have a charge, positive or negative. And the other feature that they can have is momentum or rotation. So a rotating black hole is a very interesting object, because if an object is rotating, if a massive object is rotating, it actually drags the space-time, basically the space-time thingamajig, which is really difficult to concept by itself, but it drags it. Ooh, that was fast. Okay, so 7 millimeter black hole is Venus. So essentially, this Venus, as it spins around, it will drag the space-time around it. So the space-time around a spinning black hole can actually spin faster than the speed of light, which is really mind-blowing. It's the only thing that moves faster than the speed of light is essentially space-time, which actually is the reason why we can actually create Star Trek-like warp engines. So warp engine essentially it warps or stretches space-time, and as you stretch the space-time, it can actually first of all, it can move it faster than the speed of light, and second of all, it can actually make things move through space-time a lot easier. But warp engines is a very difficult concept. Even though NASA is actually currently working on a practical warp engine, there's actually quite a lot of articles about how they're trying to find one, because theoretically it's possible to make a warp engine, but unfortunately the mass required for this warp engine to work currently would have to be massive Jupiter, which is just impractical. So they're trying to find something that will make it more practical, because you can actually create a warp engine and move at speeds faster than the speed of light. Okay, so next on the list is Mars. Mars, you're going to be a little bit smaller than Earth, but probably a little bit bigger than Mercury, close to Venus, but a little bit smaller than Venus. And as I'm decreasing the radius of Mars, I'm going to talk about another fact, and that's the fact that, well, black holes actually, or really any massive objects, but specifically black holes, they slow down time as you approach them. So this is something that if you've watched Interstellar, you probably got to experience, because it does talk about the relativity and Einstein's ideas. But essentially, as you approach the black hole, your time will slow down. And here we go, Mars is a black hole. It's actually really, really tiny, so I can't even see it. Now, what I was about to say is that basically, this is a very important fact. As you approach the black hole, the time slows down. Or not the time for you, but the time around you will slow down. And this is a fact of dilation, and essentially Einstein's theory of relativity, where he basically speculated that the faster you move, the more time around you slows down. And because of the gravity near a black hole, as you approach it, your speed will increase dramatically until basically close to the speed of light, which means that everything around you will slow down in time. So let's just say, if you're, let's start making another black hole. Where's my gas giant? Jupiter. There you are. This one will probably be a little bit bigger than most other black holes. So essentially, as you are approaching the black hole, everything around you will seem like it slows down in time. Now, I'm not going to explain why yet. Maybe in some future videos I'll explain the theory behind relativity and all that. But essentially, it will slow down until everything will seem like it stopped. But you will actually not notice anything. As you pass the black hole, you will not notice anything different. You will just notice that everything almost paused at some point, and then it kind of just disappeared and doesn't really make sense anymore. And at this point, you'll most likely basically be dead, because as you approach the black hole, it will stretch you so much that all your subatomic particles will essentially separate. Now, for a person outside of the black hole, looking at the person going inside the black hole, things will seem a little bit different. As the person approaches the black hole from as you're looking at it from the outside, well, there you go. Jupiter is 2.82 meters. in terms of size, radius, and this is a black hole number 5 or 6, 6 I think. Next on the list is Saturn. And so yes, as you are approaching the black hole and the person from Saturn is looking at the person approaching the sun, what you will see is, you will see some interesting stuff. You will see this, the person is actually, or their clock at least, slows down. So their time passage will slow down and they will move in slow motion, slower and slower and slower, until at some point, what will happen is, they will just pause. To you, if you're looking at them as they're approaching the black hole, they will just pause in time forever and ever. But in their reality, things will not be the same. So for you, it's actually a kind of a visual illusion because you're not receiving their light anymore. Basically, you're not receiving any information from them. And essentially what you see is, you see what you saw last. You see their last kind of a frame of reference where right before they passed the event horizon, you'll see them in that particular moment. But in reality, though, they of course have passed the event horizon. Nobody really knows what happened to them. All right, Uranus. Let's see if you're going to become a much smaller black hole. All right, Uranus finished, and we have one planet to go, which is Neptune. And essentially, I think those are some more important facts or misconceptions about black holes. And I guess the big ones are, that they're not really funnels. They're actually spheres, and they do have size. They're not infinitely small. They can be basically as big as you want them to be. There's no limit to how big they can be, but they do have a smallest possible size, which is actually something called Planck's length, which is a physical kind of a property of matter. And essentially, look how big and black this is. This is called the lensing effect. This is actually how we see black holes. The reason we know they're there is because the light around black holes actually bends like this. So sometimes if you look in the sky for a longer period of time, you'll see this kind of effect in the sky. And so yeah, so basically this is the idea behind black holes. They can have a small size, but no bigger size. They can have as much mass as they want to have. They have charge. They have a momentum, so they can spin. And this right here is, okay, sun shouldn't be so bright. I don't know why it's so bright. This is essentially is a solar system of black holes. And look at how beautiful it's going to be. It's just going to be spinning normally like it was spinning before. Like nothing's happening. But essentially this is a completely black solar system. Oh, and another thing is that black holes are not actually black. They do emit stuff, so you can actually detect things. Sometimes it's even called noise or basically different types of radiation. We don't really, because the closest one to us is kind of far away, we don't really have any physical proof yet, but theoretically there's quite a lot of radiation they emit, specifically blackbody radiation and Hawking's radiation. And in theory, or I guess in practice, or I'm not sure if it's in theory and practice, but basically, if we were to make a solar system of black holes just like this, it would really only last about a few minutes. After a few seconds, few minutes, most of these planets would evaporate. They would create a massive amount of energy of Hawking radiation, and they would release all of this energy almost instantly, or at least very fast. With, I guess, Jupiter lasting a little bit longer and then Sun lasting maybe a few hours. And all of this would basically become energy. These black holes would evaporate because for you to have a very stable black hole, it has to be at least 20 times the mass of Sun. So when our sun is really old, it will not actually become a black hole. And I guess that's another misconception. Our sun will not become a black hole. It will expand and then will collapse on itself. And essentially it will actually throw out a huge amount of material, creating a supernova. And inside of it, right in the center, you'll have something called a white dwarf, a very small star that will actually stay there for quite a long time. But it will not become a black hole because it just doesn't have enough mass to collapse on itself and to create this perfectly shaped black hole. Anyway, so I think this is it for me and my black hole analysis slash facts slash misconceptions. Hopefully this was helpful, and hopefully now you know how to create black holes in Universe Sandbox 2. Thank you for watching. Please subscribe and game you later. Bye bye.